Back. So we are now on section 4.2 of chapter 4, the definite integral. Okay, definite integral. So let's see what we have seen so far. We have seen that a limit of the form limit n approaching infinity, summation I going from 1 to n, f of xi star delta x. Okay, summation means just listing out each one. So when I equals 1, I get fx1 star delta x plus I equals 2, fx2 star delta x plus dot dot dot. The last one is I equals n, fxn star delta x. Now what was delta x? Delta x is the width of a rectangle, a small rectangle under your curve. What was fx? What was xi star? Xi star was a chosen point in your sub interval for each rectangle. Either it's a left end point or a right end point or a midpoint or any point of your choosing. Hence the star, a chosen point in your sub interval, ith sub interval. So I represents the ith rectangle, first rectangle, second rectangle, 10th rectangle. I would be 1 or 2 or 10 and so on. Xi corresponds to that point on the x-axis whose height is determined by f. Okay, xi star. Now you have taken the summation. This is for n rectangles. You have chosen, you have made n rectangles, found the width of each rectangle, chosen a point in each rectangle, chosen a height corresponding to f for that number, and then height times width. This is area of one rectangle. Summation means take the sum of all those areas. You get some number. Now increase n means increase the number of rectangles. Keep increasing the number of rectangles to go to infinity. That is what gives you area under your curve. Okay, so this summation arises when we compute an area. We also saw that it arises when we try to find distance traveled by an object. Turns out the same type of limit occurs in a wide variety of situations, even when f is not necessarily a positive function. Okay. Definition of a definite integral. If f is a function defined on an interval a to b, okay, that's what it means. X is between a and b, including a and b, less than or equal to less than. So your function f is defined on a to b. We divide the interval ab into n sub-intervals of equal width. What is that width? Well, big number b minus small number a, the whole over n. That's the width of each sub-interval. Let x naught be a, that is the leftmost point is called x naught or x0, and the rest are all cut points, x1, x2, so on, until the last number is b, xn. These are the endpoints of these sub-intervals, and let x1 star, x2 star, so on, xn star be any sample points. Sample points means any chosen points in these sub-intervals. So xi star lies in the ith sub-interval. Okay, this is the ith. Then this is important, guys. The definite integral of f from a to b, it's written like this with a long s. A to b f of x dx, it is this limit. Okay, now this is for any function. So this is what we have been seeing for rectangles. The only, why would you have such a definition? Because in the previous cases where we saw, all the rectangles were standing above. You see, all the rectangles were standing above the x-axis. Well, you could have something below also. Why would you have only above? Well, you have rectangles only above when your curve is all greater, is above the x-axis. You see? Here, your rectangle, some of them go below because the curve could go below. All right. Hence, you have a separate definition. Okay. So that's all. It's the same thing as we have done before, except now my curve could be above, could be below, whatever. Whatever be my function defined from A to B, I can define such summations, okay, such sums of so-called area. If you're above or below, you still have some kind of area. Take the limit as n approaches infinity. Okay, that is what is called definite integral. All right, provided that this limit exists. Well, this limit has to exist. If it doesn't, you say integral does not exist, and gives the same value for all possible choices of sample points. That is important too. Your xi star, the chosen numbers in each subinterval, should be immaterial. You should be able to find the limit. If it does exist, we say f, the function f, is integrable on closed AB. The symbol this, right, was introduced by Leibniz and is called an integral sign. So this is called integral. Okay, it is actually an elongated S and was chosen because an integral is a limit of sums. All right, next. In the notation integral a to b fx dx, fx, that is the object inside, is called the integrand, and a and b are called the limits of integration. A is the lower limit, b is the upper limit. From now, the symbol dx has no meaning. For now, dx has no meaning, okay, by itself. This is all one symbol, okay. The dx simply indicates that the independent variable is x. The procedure of calculating an integral is called integration. All right. So this is all one symbol. What does it say? It is short form of the following phrase: integral from a to b of fx, where x is the independent variable. All right. Integral a to b fx dx. That's how we read it. Okay. Now, so finding that limit, this is same as finding the integral, and that process is called integration. Okay. We need to see a few examples before you understand more. Until then, keep reading. Note 2. The definite integral, integral a to b fx dx, is a number. It does not depend on the variable x. So the final answer is going to be a number, or you say it does not exist, because this is going to be a limit. Okay, x is not important. Instead of x, you could even write t, or you could even write r. The meaning remains the same. The summation, okay, summation I going from 1 to n, f of xi star delta x, is called Riemann sum. Okay, this summation, sigma I going from 1 to n, fxi star delta x, it is called Riemann sum. Riemann sum is named after the German mathematician Bernhard Riemann, 1826 to 1866. So definition 2 says that the definite integral of an integrable function can be approximated to within any desired degree of accuracy by a Riemann sum. All this means is area under this curve can be approximated by these sums of these areas. Sums of these areas is called Riemann sum. So more cuts you take, that is thinner your rectangle, closer you will get to the area under the curve. We know that if f happens to be a positive, then the Riemann sum can be interpreted as sum of areas of approximating rectangles. All right. We see that the definite integral a to b fx dx can be interpreted as the area under the curve y equals fx from a to b. If fx is greater equals 0, so you're all above the x-axis, the integral a to b fx dx is the area under the curve from a to b. Now, suppose your function is partially above, graph is partially above and partially below. If f takes on both positive and negative values, then the Riemann sum is a sum of the areas of the rectangles that lie above the x-axis and the negatives of the areas of the rectangles that lie below the x-axis. Okay, so when you are partially above and partially below, what is the integral? Well, you take areas here, they are all positive, and subtract areas here. So all the negative areas are below, positive areas are above. So this minus this. Okay, that is what it means to say integral. Okay. When we take the limit of such Riemann sums, we get the situation illustrated in figure 4. A definite integral can be interpreted as a net area, that is, difference of areas. Integral a to b fx dx is a1 minus a2. What is a1? a1 is the area of the region above the x-axis and below the graph. So this plus this is a1. What is a2? a2 is the area of the region below the x-axis and above the graph. So this is my graph. This is a2, so I'm below. So this area plus this area minus this area is the integral a to b fx dx. Okay. Note 4. Although we have defined integral a to b fx dx by dividing the interval a to b into subintervals of equal width, there are situations in which it is advantageous to work with subintervals of unequal width. So, if the subintervals widths are delta x1, delta x2, delta x, so these are the width of each rectangle. They could be different. We have to ensure that all these widths approach 0, okay, in the limiting process. So instead of saying n going to infinity, you can say the width, maximum width is going to 0. That is, your rectangles are getting smaller and smaller, rather thinner and thinner, okay. Maximum width is approaching 0 means your rectangles are getting thinner and thinner. So integral a to b fx dx is limit maximum of the width going to 0, summation of the sum of areas. Note 5. We have defined the definite integral for an integrable function, but not all functions are integrable. That you have to know. Sometimes your function could go to infinity. You won't be able to find the area. So, the following theorem shows that the most commonly occurring functions are in fact integrable.